Hi y'all, this is section 3.2, the numerical definition of derivative. So, as a reminder, the derivative is just the instantaneous rate of change, and graphically it will be equivalent to the slope of the tangent line. Okay? So if the function is increasing and our tangent line would then therefore also be increasing, we know our derivative should be positive. If the function is decreasing, then we know our tangent line would also be decreasing, and we know that the derivative should be negative. Okay? Function increasing, derivative positive. Function decreasing, derivative negative. It's a huge concept that you need to make sure you have down this year. Okay? So we're going to revisit the spaceship problem. It's the exact same problem that you guys looked at in section 3.1. Okay? And I basically summed it down to the steps that I want you to use. Okay? Please do not use your calculator for this section unless you want to check a value or check what the graph is going to look like. But other than that, please do everything by hand just like I am in the notes. Okay? So we have this spaceship is approaching a far-off planet at time x in minutes, so x is in minutes. And after its retro rockets fire, its distance, f of x, so this is the distance away from the surface of the planet, is here. And the distance is in terms of kilometers. Okay. It's given by this function here, x squared minus 8x plus 18. So that's what the picture would look like. Okay. So when you did this in section 3.1, they asked you a whole bunch of questions about x equals 5. And so that all of that was all about the derivative of this function f of x at x equals 5. We're going to do the exact same problem, but I'm going to take a different point. We're going to figure out the derivative at 6 of this function. So first off, what does f of 6 equal, and what does that value represent? So these are tick marks are 1, so 1, 2, 3, 4, 5, 6. So right here it's 6. I want to know what f of 6 equals. So if I plug in 6, what do I get? So if I plug in 6, what do I get? Okay, that would be f of 6. And then what would it represent? Okay, so plugging in 6 here, I got that it'd be 6 squared minus 8 times 6 plus 18. And so when I did my math on that, I ended up with 6. So it happens to be the same output as it was the input. Realize that's just a special case. That won't always occur. So that should have been right here at 6. 1, 2, 3, 4, 5, 6. Pretty close. Good. Okay, so 6, 6. And then what does that mean in terms of the spaceship? It means that 6 minutes after the retro rockets fired, the spaceship was 6 kilometers away from the surface of the planet. Okay, so after 6 minutes, they were 6 kilometers away. Okay, I didn't write it, but I said it. Please write it. All right, part B. The average rate of change of the function f of x from 6 to any value of x. So basically what I'm trying to say here is if you have your value at 6, you knew you were right here. If we look for the average rate of change from 6 to some other given value of x, no matter what that x value would be. Okay, so if we have this continues on up, that would be the value, and the output of that value, all we could call that would be f of x. I want to know what the average rate of change over that interval would be. So basically it's just, anytime you see average rate of change, remember that's just the slope formula. You're saying, what would the slope be if I connected those two dots? So that would be the output that I get when I plug in x, which was f of x, okay, minus the output that I get when I plug in 6, which was f of 6, which I know happened to be 6, but I'm going to save the value for the next step, over the difference here, x minus 6. Okay. So that's the average rate of change from 6 to any given value x. Okay. So you should recognize that as a difference quotient. Okay. So we're going to take that information, and for part C, we're going to call that equation r of x, standing for the rate of change function. So let's go ahead and give that a name, that r of x equal f of x minus f of 6 over x minus 6. That is standing for the rate of change from 6 to any given x value. Okay. So what I want us to do from here is simplify completely. So we're going to take this guy and simplify it, then we're going to graph r of x. Okay. So r of x, we're going to replace what f of x is right here. So f of x was that trinomial, x squared minus 8x plus 18 was f of x. Minus f of 6. We're going to plug in what we got when we plugged in 6 into the original distance function, which was 6. All over x minus 6. Notice the x's don't get replaced. Okay, we're moving from 6 to some given x value, so x is the other input. Then this should feel a lot like what we've already been doing. We're going to simplify. So positive 18 minus 6 will give us x squared minus minus 8x plus 12 over x minus 6. And then we should factor the top guy, and the bottom guy is already x minus 6. So to multiply to get to 12, add to get to negative 8, must be x minus 6, x minus 2. Okay. Now here's this key step, right? Remember, if you cancel out a common factor on top and on the bottom, that will create a hole in your graph. Okay? So we can say that r of x equals, x minus 2. But remember, if you cancel something out, that is your restricted value. You know that x cannot equal that value. So you need to state this here. If r of x equals x minus 2, as long as x does not equal 6. Okay? So we know that that is the equation for the average rate of change from 6 to any given x value. Okay. They also asked us to graph, so let's go ahead and sketch this. So if we look at r of x, and we know it's going to equal x minus 2, so we know we're down here at negative 2. We're going up one to the right one, up one to the right one, up one to the right one, so we know it looks like this, except when we get to 6, we're going to have a hole. Okay? So the rate of change from 6 to any given x value will equal x minus 2 as long as x does not equal 6. Okay, so if we look at this picture, this is going to help us answer that next question. Now if we take the limit of r of x as x approaches 6, so the question here is taking the limit of r of x as x approaches 6, what do we get? Okay, that value will be the exact value of the derivative of f of x at x equals 6. Okay, basically we've just used the definition of derivative without even realizing it. Okay, so if we look back at this picture, and we want to know the limit of r of x as we get closer and closer to 6, we get our fingers out. What are we getting closer and closer to? We're getting closer and closer to the output that would have been sitting there. Okay, remember that r of x reduced down to x minus 2. So if I plug 6 in, 6 minus 2 should have given us 4. So I know that the value that I'm getting closer and closer to is indeed 4. Okay. So what are the units of this derivative? If we think about what r of x equaled, remember r of x, if we go back, r of x equaled this stuff, f of x minus f of 6 over x minus 6. So let's talk about the units. These were the distance units, so those were kilometers. Okay. Over x minus 6, those were your time units, and those were minutes. So we know our derivative value should be kilometers per minute. So here, the units would be kilometers per minute. Okay. And then what is the meaning of this value in terms of the spaceship? Realize that if you have a distance versus time graph and you're looking at the derivative, that will give you the velocity at that given time. So this is saying that the spaceship was traveling, or the spaceship's velocity, let's do that. Spaceship's velocity was 4 kilometers per minute at, and it's really important here that you get both the units for the velocity and the units for the time. It's traveling this speed at what time? Was 6 minutes. So at 6 minutes after the booster rockets were fired. Alright, so for letter E, so if the derivative of f of x at x equals 6 is, now the blank is the value that we just got for the limit problem there. So the derivative was 4. Okay. Then we should be able to draw on the tangent line to f of x at x equals 6 and be able to write an equation of that tangent line. Okay, so remember that if we go back to that original graph, zoom, something along those lines, and we look here at 6, remember we were there at 6, 6, right? If we draw on the tangent line at that point, okay, we now have figured out exactly what the slope of that tangent line is. Okay, we can actually write the equation of that line. So, anytime it asks you to write an equation of that line, I want you to jump right into y minus y sub 1 equals m times x minus x sub 1. Okay, you're going to do this so often throughout the year. So you need to remember that you need 3 inputs: the x, the y, and the slope. So x comma y is the point at which you're tangent to, okay, along your curve. In this case, it's 6 comma 6. So 6 comma 6. Then you need the slope of that line. In this case, the slope we found by taking the limit of the average rate of change from 6 to x. So we figured out the slope of that line was 4. So if you know the slope in a point, you can just plug it straight in here and go y minus the y1 value, 6, would equal 4 times x minus the x value. In AP Calculus, you can totally leave this as your answer. That is an equation of a line. If you choose, you can distribute the 4 and solve for y, and you get y equals 4x minus 18. Okay. Either of those would be fine. You don't have to do this. But if you'd want to double check and make sure that your answer was reasonable, hopefully you could see that that is pretty reasonable, that would be crossing down there at negative 18 and had a slope of 4. And it was tangent to our graph of f of x at x equals 6. Alright, so finally here, officially, what is the definition of derivative? So what we just did right there was the definition. Okay, that was specifically for x equals 6. So if we look for any given value, okay, notation, by the way, here we go, finally, formally, f prime, so we'll call that f prime of your c value. That means the derivative, okay, the derivative of f at c. So f prime of c is how you read that out loud, okay, will equal. So the derivative at c will equal the limit as x approaches c, so the limit as x approaches c, of that average rate of change from your given c value to any x value to the right of it. So we're going to call that output f of x minus the value that we get when we plug in c, f of c, all over x minus c. So you totally need to understand this, and you need to be able to write it down, and basically need to memorize it. Okay, it's a difference quotient, and we're taking the limit of this difference quotient. Okay. So example number 2, I gave you the same old problem we've been working on, the spaceship problem, but now I'm asking it in a slightly different form. So I'm saying use that definition of derivative to calculate f prime of c exactly, and then I want you to write the equation of the, looks like I lost it, tangent line. Okay, so same old function, x squared minus 8x plus 18, but this time we're looking at c equals 3. Okay, so big idea here, because the function was decreasing, I know that my tangent line, if I had drawn that perfectly, should have a negative slope, therefore my derivative should be negative. Okay, so let's keep all of that in mind. So, letter A, use the definition of derivative. Alright, so definition of derivative, let's practice writing it out a few times. F prime of c will equal the limit as x approaches c of f of x minus f of c all over x minus c. Okay. So our c value for this problem is 3, so we're going to plug in 3 everywhere we see a c. So this is the limit as x approaches 3 of f of x minus f of 3 all over x minus 3. So now we're basically where we were for part C on the last problem, or I don't know what part, but this is now already part of this limit question. Okay, so when you have this form, you technically need to keep writing that limit until you can actually plug it in. Okay, so let's go ahead and plug in our values. X squared minus 8x plus 18 will go in for f of x. So x squared minus 8x plus 18. And then this time we're minusing our f of 3. And f of 3 I don't think we ever found. So let's go ahead and do that. Let's figure out exactly where that dot is. So f of 3, or use your calculator if you need to. 3 squared minus 8 times 3 plus 18. Double check me on this. I think I got 3. Interesting. 2 random examples. They both happen to have the same input and output. Sorry about that. So f of 3 is 3. So our output here was 3. All over x minus 3. Okay. And combine those like terms. Still the limit as x approaches 3 of x squared minus 8x plus 15 over x minus 3. Okay, so all of that is what we're trying to take the limit of. Maybe we should pause and stop for a second and try to plug in 3 and see what we get. Okay, we would get 0 over 0 or indeterminate form, which would mean we need to do something else. Our something else is to factor. So let's go ahead and factor. So we have x minus 3 times x minus 5 over x minus 3. The x minus 3's will indeed cancel. So we have the limit as x approaches 3 of x minus 5. Now, if you were just working with this function, you would have to state x minus 5 comma as long as x does not equal 3. But because we're already in the limit form, we're already talking about the limit as x approaches 3, now you can literally just plug in 3. And this has been the first step where I could plug in 3 and it wouldn't give me 0 over 0. So right here, if I plug in 3 in for x, I get 3 minus 5, and I get negative 2. Okay. Remember what this was equal to? All the way back up here was f prime of c. Ooh, and I should have written this right here. F prime of, I didn't plug in my 3 over here. F prime of 3 equaled this. Now all the way down, that is what my final answer is. F prime of 3 equals negative 2. Okay. Now remember, we started this problem by saying that our derivative should be negative because the function was decreasing at that point. Okay. So I'm glad we got a negative. And for part B, we want to write the equation of that tangent line. So if I now know that the slope of this line was negative 2, okay, and I know that it was going through the point 3, 3, I can jump right into my equation of the tangent line. So, part B, I'm going to say y minus y1 equals m times x minus x1. And we've just figured out that our slope was negative 2. And our points that it went through was 3, 3. So y minus 3 equals negative 2 times x minus 3. Perfectly fine answer. If you'd like to double check it against the graph, so that would be a positive 6, and we'd be adding 3 to that. So y would equal negative 2x plus 9. So negative 2x plus 9, hopefully that is reasonable, that we were crossing, if we had drawn this perfectly, that we had crossed up here at 9 and had a slope of 2. Okay, the tangent line at that point. But function was decreasing, therefore our derivative was negative. Okay. I know it's getting a little long, y'all, but let's keep on going. Let's try this last guy. So new function finally. I give you f of x equals slightly longer cubic function, and we're looking at specifically c equals 4. Okay. My tick marks here are 1, so this is a 4. And here, though, these tick marks are 10. So 10, 20, 30, 40, 50, 60, I think was my point right there. You can see 0, 46 is going to be that point right there. Okay. So here at 4 is what this whole problem is all about. I'm going to use the definition of derivative to figure out exactly what the derivative is at 4. I don't know if I've said this yet. This is not an estimate anymore. This is the exact rate of change at that point. Okay. So definition of derivative. Let's go ahead and jump in. F prime of whatever our c value is will equal. Don't forget this part. This is actually an answer to a quickie question. The limit as x approaches your c value will need to go here. And then it's f of x minus f of c all over x minus c. I purposely left off all my c's in the definition so I can just fill it in and not rewrite it. You can use that as well, as long as you know that these are all c's. Okay, for the c values, this is a numeric derivative, which means it's only good for that specific c value. It won't work for any other value. Alright, so once you have, there's your definition of derivative for specifically c equals 4. Now we're going to plug that stuff in for f of x and simplify. So the limit as we approach 4, that was x cubed minus 4x squared minus 9x plus 46. And we're subtracting f of 4 all over x minus 4. I don't think we did this together yet, but when you plug in 4, so 4 cubed minus 4 times 4 squared, you should get 10, which hopefully makes sense. Very nice. So f of 4 was 10. If you need to use your calculator for that, feel free to, or you could punch it in and make sure, or plug it in, make sure you get 10. Okay, so that was this guy here, plus 10. And so we're left with the limit as we approach 4 of x cubed minus 4x squared minus 9x plus 36 divided by x minus 4. So again, at some point right now, you should plug in 4 and see what you get. If you did it right, you get a 0 over 0. Indeterminate form, we need to do something else. Or something else in this case is to factor. But, ooh, maybe this is factorable by grouping. Let's see if we can group this up. How nice if it is. If it's not, we have to use synthetic division. So in my notes, I hadn't caught that it was factorable, but I think this is. So x squared times x minus 4. And then 9x plus 36, there's a negative 9 in common. So I'd have a positive x and a negative 4 all over x minus 4. So this is still the limit as we approach 4. And then we can regroup and say that that actually equals the stuff inside the parentheses, x minus 4, times the stuff that we factored out, x squared minus 9. And feel free to use synthetic division if that didn't make sense, over x minus 4. So now the x minus 4s will cancel, So I'm left with the limit as we approach 4 along x squared minus 9. And now I can finally plug in 4. 4 squared minus 9. 16 minus 9 would give us 7. So we're left with the derivative f prime of 4 equaling 7. And from here, we want to write our equation of our tangent line. So our equation of our tangent line would be y minus y1 equals m times x minus x sub 1. This is their derivative value. So the slope is 7. And the derivative at that point will equal the slope. And then the point that it went through was 4 comma 10. So final answer here for the derivative of the slope of the tangent line, or the equation of the tangent line, y minus 10 would equal 7 times x minus 4. I think this got really long, so I'm going to go ahead and stop there. Please write down any questions that you have, and good luck.